A number of quite nice quality analog meters that are available on the internet are these TMK sort of circa 60s, 70s Japanese made analog meters. Good quality, well built, and there's quite a few of them available second hand on eBay. I bought this one probably a couple of years ago, and I think I showed you a review on it before, and you've seen them before. They're in nice condition. They're a good movement. The scale accuracy is very good for a meter of its type. But I've picked a couple more up. I picked this one up a couple of days ago on the internet. Sold as spares repair, not sort of working. Got a slight crack in the corner there. I've just spotted that, but funny enough, I've got a few spares for these. Paid very little money for this one. I actually bought two. They had two in non-working condition, or sold as non-working condition. Cosmetically in very good shape, so that's good. No cracks in the case or anything. Usually have the little rubber feet on the bottom of these, but they're missing. But that's not the end of the world. You know, they're a pain in the arse anyway, because they're always covering the screws. That means you had to pull them out to get to the access to the screws. So I probably just stick some pads on the bottom or something like that. So it's a 20,000 ohm per volt range on DC, and I think it's 10,000 on AC. You got various ranges from 2.5 volts AC up to 500 volts. And 1 kV with its own dedicated connection. We've got amps up to 12 amps DC, which is nice, but we've also got up to 12 amps AC as well, which is also good, because it's actually got a current transformer built in. There's two models of this. The other one has the output connection. For those who don't know what the output connection actually does, it's basically a decoupling capacitor, so you can measure the AC signal of, for example, a valve radio. Before the transformer, it will block all the DC coming from the anode, and it will just give you the AC component on the meter, which is pretty useful. We've got a continuity tester, which is basically just a mechanical buzzer, which is quite quaint when it works. Obviously this one's got no batteries in it at the moment. So we've got 250 millivolts up to over 250 volts, or 1 kV on its dedicated connection as well. Fairly well protected. It's got diode protection on the meter, which protects the meter from excessive overvoltaging and damaging of the coil. It has I think it's got a thermistor as well, actually, for some sort of protection. So this is a nice meter for its day. You know, it's not the same range as like the Simpsons and things like that, or the Avos, but it's a very good meter, and it's actually a much more usable size, because obviously a Simpsons taller than this, and an Ava's even bigger than that. So bought this for spares and repair. Let's open up the back, have a look inside, and see what we've got. Basically, it's 4 posi screws, just covering off all the back off it. So inside we've got basic sort of through-hole technology, obviously of the 70s. This one actually is in pretty nice condition, as you can see. But you will spot here, and I've actually cleaned this up, I've opened this up before, this resistor here was open, 340 ohms, and that's what's really nice about it. It's actually marked on the printed circuit board, the actual value of the resistor, and this 3K78 which has got burnt. Possibly part of the current shunt circuitry, but we're not sure. Also, the other thing I spotted, it's not on this meter, it's on the other one. Here's our DC current shunt here with this bar across here. The transformer here, can you see that? Yeah, that green transformer is the AC current transformer for measuring the AC. Pretty nice condition inside, you know, no sign of any battery leakage, unlike the second unit that I've got. Here's the buzzer for the continuity, so it's a proper mechanical buzzer, none of your piezo or piezo sort of stuff. It's, you know, a mechanical buzzer that actually buzzes. Connections here to the meter, where are we? Connections here to the meter, and series resistors to calibrate the meter. You'll see here that the fuse is popped, so obviously someone's given it some voltage at the wrong end, possibly in the ohms range or something like that. So the first thing we need to ascertain really is the movement okay, because that's the first thing that's going to scrap the meter. If the movement's open circuit, this meter's scrap. It should be pretty well protected because it's got series resistors, and it should have some diode protection. Here we go. I think this is that might be actually the bridge rectifier, but there should be some diode protection on this meter as well, maybe built internally. So the next step to do is I'm going to connect it up to some DC, low voltage DC supply, and see if we've got any movement on the meter. Okay, on these probes here I've got 5 volts, so I'm going to connect these 5 volts to the 10 volt range, and we're expecting to see half deflection on the screen. Now if we get that, this will ascertain that the meter movement's okay, and that's a good start, and then we can start to go around and check the resistors and see which ones are open circuit and which ones are damaged. So let me zoom you in a little bit so you can see a bit easier on the meter. So let's give that some. So this is 5 volts. We've got nothing on the meter. Okay, so first thing we need to check is make sure as the fuse has blown, it's not. I don't know if that fuse protects the current ranges as well. So I'll pop the fuse out. Okay, and let me find another fuse. Pop that in, and we'll try again. Okay. I found a fuse. Let's just pop that in just to see if we get any meter deflection. It could be that these actual resistors are in series of the meter as well. Possibly the meter isn't damaged or written off yet. But let's just quickly try this. I'm going for dinner. Let's stick 5 volts across it again. There we go. Meter's okay. Brilliant. So the meter's, we've got 5 volts, just under 5 volts reading there. So that's good. Yeah, just under 5 volts. I don't know exactly if we're on 5 volts anyway, but that looks good. So we'll move on to checking those resistors next. Right, what I'm going to do is I'm going to check this resistor here that actually is an open circuit, but it looks like it's had a bit of burning, and it could have just been burnt because of the resistor that was nearby. So let's just check that. So this is a 3.78K. So let's have a look on the fluke and see what the fluke reckons it is. Okay, perfect. So that resistor's fine. So all we need to do is change this 340 ohm resistor. So what we've got to do is find a resistor here that's 340 ohm, pop that in. Well, and then we'll do a sort of range check on it, see if it works anywhere, sort of like reasonable calibration. And if it does, great. And if not, we might need to sort of recalibrate a few things. But initially, it looks like it's probably just that 340 ohm resistor, which is probably a current shunt resistor. Never, can't tell really, but we'll get that replaced. See what we get when we power it up. Unfortunately, there's no such thing as a 340 ohm resistor, and that's not the standard value. It's what's the equivalent is a 330, which should probably be okay. But what I have here, we've got a 680 ohm. So if I put the two 680s in parallel, well, I should have 340 ohms, which would be brilliant. So what I'm going to do is I'm going to tack these two together, parallel them up. So basically, just all you do is these are bigger power resistors, but they're only 10%, 5% tolerance, so they should be fine on something like this. I think they're 1% on the spec for this meter for the resistors. But what we'll do is I'll parallel these two resistors up. So I'm just going to connect it up on the meter and just see what we get. Now we can actually sort of like go through my resistor stash and see if we can find something that's a bit closer, but just see what we get when we measure this. And we've got 342 ohms. I think that's good enough. 342 ohms, and it wants 340. That's pretty good, isn't it? So let's get that installed, and then we can do a power up. Okay, not a thing of beauty, but certainly a thing of functionality. It's connected up. We've got the resistor back in place. So really, I think the probably next thing to do is actually put this meter through its paces. I don't know, I might have a battery in here to check the ohms range. So let's get the back on it, so we can find a battery, and then we'll just do a basic voltage test, certainly on the DC, see if anything's working reasonably well. There's no signs of burning on any of these resistors, that's good. Here's the bridge rectifier I was talking about earlier. That's the rectification for the AC, and that's obviously done post the attenuator because they're only germanium diodes, so they're very low voltage diodes. And as I pointed out earlier, those two diodes there are probably across the meter. Actually, I can see they are now, and they are back to back. So basically, you put a diode one way and the other way. So you put the cathode and the anode joined together, and then you put them across the meter. So basically any voltage exceeding about 300 millivolts, these diodes will start to conduct and protect the meter, and it's a good protection clause for these sort of these old analog meters where their resistors are being zapped and voltages being put out the wrong way. Okay, so let's give it a quick run through, see if it works. And just a note on these meters, just going to install the batteries and look at the connection, and usually you've got positive, negative, negative, positive, because they're wired in series to give you the 3 volts. It's not that at all, actually. If you look, so we've got a link, joining link here and joining link here. These batteries are wired in parallel. So these meters will run with one battery fine, as long as it's a reasonably high capacity battery, and then probably a Duracell will be fine, Duracell Ultra, something like that. Not sponsored by Duracell, I wish I was. So we can actually run this on one battery, and you don't need to put 2 batteries in it. And that's what I was about to do. I found 2 batteries, but unfortunately they're different, probably different capacities, because one's an Energizer, one's a Duracell. So I don't want to run those 2 in parallel. But let's run one on its own, get the back on and see what we get on the ohms range. Okay, so let's start on the ohms range. So we'll null our meter to 0, and we'll so we're on the ×1 ohm range. I haven't got a proper connector on here, but it's making good connection, or reasonably good connection. So let's go to 10 ohms. We should have our meter come up to just about here. So let's go 10 ohms. Okay, try 20 ohms. It's lagging behind a bit, isn't it? 30 ohms. Okay, maybe not perfect calibration on ×10 ohms, so let's try it on the 10 ohm ×10 ohm range rather than ×1 ohm. So let's bring it up to 0 again. Pot's a bit noisy, so let's go 100 ohms. Not great. 200. Okay, we've got calibration error here. 300 ohms. 4, 5. Okay, so we've got, it is coming back slowly, but it's hanging up a bit. Yeah, so it looks like we've got a problem here with our calibration on the meter. Now I'm not sure if this is noisy pot or a slightly sticky meter. It could be, actually it looks like it might be just a noisy pot. So let's just try that again. This is a Jim Lindenaris situation where you fix something and then you actually then go back and actually repair the bits that are faulty after you've done the calibration. Okay, so let's try it again. Yeah, it's something's very touchy here. Okay, let's pause this and we'll have a look again. Okay, I think we're going to need a bit more attention before we start trying to calibrate it. You watch the meter 0, so it's on the ohms range. It was 0 to 0, and just touch the switch. Okay, you see the classic sign of a dirty switch. So let's get the back off again. I should have done that in the first place, really. I don't know why I didn't do it, actually. I didn't think. So let's get the back off it, give the switch a clean up, and see if we can clean that erratic movement up. Okay, I'll clean the switches up and the pot up and give you a better idea. I'm trying to get you central to the meter. It's not going to be perfect. You're going to get a bit of parallax, but let's try this and see what it's like then. So we're on the ×1 range, and we'll go 10 ohms start off with. No, we won't. There you go, 10 ohms. That's pretty good, isn't it? 20, 40, 50. Brilliant, that's working perfectly well. 60, 70, 80, 90, 100. Bear with me. That's 100. That's clearly working fine on that range. Let's go ×10 range. So let's go 100 ohm. No, I'm not. 100 ohms. There we go. 200, 300, 400, 500. That's working well as well. Let's go to the ×100 range. Might reset to 0. So let's go 1K, which is 10, 2K, which is 20, 3k, 30, 40, 50, etc. 60, 70, 80, 90. Pretty good. That's 90k. So it looks like the ohms range is working pretty well actually. So let's try it on the 1k range. Obviously it hasn't got time to 10k range because you need a 9-volt battery for that. So let's go 1k again. Yep, 2, 3, 4, 5, and let's go 10k. And not 10k, 20, 30, 40, 50. Meter's working perfectly well. Now, I was telling you about that mechanical buzzer. It's quite comical. Do you want to hear the mechanical buzzer? Really? So, that's your mechanical buzzer for your ohms range. So let's move on to volts then. Let's do a quick check on the volts range, but I'm pretty confident everything's okay now. But we'll move on to volts range, have a check of that, see if that's reasonably accurate. Right, I'm about to fit in exactly 998.2 millivolts onto the 1 volt range. We should have more or less full scale deflection. And we have. That's pretty good, isn't it? Okay, so what I'm going to do is move to the 2.5 volt range. So 2.5 volt range, for those who don't use an analog meter, you're basically looking at the 250 volt range. You're just standing or moving the decimal place to 1 point. So you can see we've got 1 volt coming in here. Let's increase it to 2 volts, see what we get. That's 2 volts there. Slightly low, but not bad. Pretty acceptable for a meter like this, I would say. Let's try it on the 10 volt range. Now this meter is calibratable, but I'm not really that bothered. I'm not going to use it for critical measurements. So we'll try it on. So we're on the 10 volt range. Let's go to 5 volts. So we should be halfway up the scale. Bit jumpy on the control. There's 5 volts exactly. Okay, we're lagging very slightly behind, but that's not bad. The 5 volts should be exactly there. We're slightly off. Let's try it on the 25 volt range. Let's give it say 15 volts. Okay, so that's about 15. There's 15 volts there. Similar sort of thing, slightly off. So it's looking like the calibration that needs to be done, if any, which I probably won't bother with, is the main calibration post the attenuator, selectable attenuator, actually up by the meter sort of section. And I think there is a resistor, a variable resistor for adjusting that. We'll go to the 100 volt range. I'm not going to go any higher than about 30 volts simply because I can't be bothered to change the power supply, but this is 30 volts. It's 30 volts. And you can see we're just slightly shy there as well. So this meter is pretty accurate and probably well within spec, but it's certainly working perfectly okay. The thing I would like to check next is the current. So we need to sort of be a little bit careful with this because obviously these things are a bit fragile. So we'll try some DC current. We can basically assume the AC works. I know you shouldn't ever assume anything, but it looks like the DC is working fine, so there's no reason why it won't be working on AC. So let me set up for current and we'll take some measurements. Right, I've set my Roban power supply up to current limit of around 500 milliamps, and so it should give us full scale deflection. That's pretty bloody good, that is. So that looks pretty impressive actually. So we'll try it on the 12 amp range, but I can only on this power supply only give you 2 amps, but that should give us basically here. So let's try it on the 12 amp range. So what you do is you short my leads out, which I'm doing on the switch on the power supply. Let's give me 2 amps. So turn that to 2 amps and put it on the where are we? Is there 12 here? DC 12 amps. So I need to go common on that connection and there. I got it around the wrong way. There you go. So this should be 2 amps. So 12 amp range is on the blue, 2 amps exactly. So it looks like there's absolutely nothing wrong with this meter. It's actually, apart from that resistor that burned and the fuse that I need to check the right rating and get it correct again. it's a perfectly working and very useful meter, and very useful for working on things like automotive wiring when you've got lots of damp wiring and stuff like that, and you can put a digital meter across a 12 volt connection with a blown fuse and it will still show 12 volts. You need a bit of loading on here, and this meter will offer a bit of loading because it's 20 kilo ohms per volt. It's much easier to work on automotive faults with something like this than it is with the digital meter, unless you put a shunt across the meter, and I've mentioned this before in some of my other videos. So this is the TMK 500TU-B. There was another version, the TM500TU, I think it was just the TU, that didn't have the 12 amps AC option, but it did have the AC output terminal, which is pretty useless on any respects. Anyone can wire a series capacitor in, it's not a problem. But to have that 12 amp AC option is a real bonus and a real boon. So a nice meter in lovely condition, apart from the little crack there that I'm not worried about. I probably will leave. Look after them. They're fragile. They're, in my opinion, they're almost as good as an Avo, probably as good as a Simpson, and you can pick them up fairly cheap. Thanks for watching.